Chapter 18 is all about what happens when you add waves together. What does happen when you add waves together? Well, the animation shows us essentially you just add the two wave functions up. Two waves on a string meet. You've got a pulse, a red pulse combined with a blue pulse. The resultant pulse is just y1 plus y2. You add them up. It's true even if one has a positive displacement and the other one is a negative. Here, the orange one is a negative displacement pulse. The resultant wave is just, that you see in black, is just red plus orange. I mean, blue plus orange, which, you're algebraically adding a negative onto a positive. So the resultant wave is just the sum of the two individual wave pulses. Mainly in this chapter, we'll be concerned with adding sinusoidal waves onto each other. One sine wave added onto another sine wave. And we'll see there's some interesting things that happen when you do that. Here, for example, is an example of a cosine wave in red added to a sine wave in blue. So the red one could be cos omega t, the blue one could be sine omega t. And I want you to notice that sine omega t is just cosine with a phase of minus 90 or minus pi over 2. So what we've got here is cos omega t in red plus cos omega t minus pi over 2. And look what the result is. You get a wave, you just get another sinusoidal wave, exactly the same frequency as the red and the blue. The difference is the phase is right in between the other two. The blue one had a phase of minus pi over 2, and the yellow one looks to have a phase of minus pi over 4, or 45 degrees, right in the middle of the two. Another thing to notice is I'm adding, they have equal amplitudes, red and blue. They both have amplitude 1. And when you add them up, you get an amplitude which is about 1.4. All these facts put together might remind us of a right triangle. If I take a right triangle whose sides are 1 and 1, I get a hypotenuse, which is square root of 2, 1.4, and the angle of the triangle is, of course, 45 degrees, giving us a clue that there must be some geometric way to add these things together that has to do with triangles. Here's another example. Now we're adding a blue and a green onto each other. In this case, the blue one is 4 cos theta. The green one is 3 sine of theta. Now again, sine of theta is cosine theta minus 90 degrees. So we add them up and the result is the one in red. The one in red is again of the same frequency as the other two. But look at the amplitude. I added an amplitude 3 and a 4 and I got an amplitude 5 out of it, giving us a big clue that must have something to do with right triangles here. Also, 53-degree phase. 53 degrees is the angle of a 3-4-5 right triangle. So clues here. Obviously, there's something to do with triangles that can be used to add sine functions together. I want to make it clear that I'm adding waves of identical frequency. Adding waves of different frequency can produce waves of all kinds of different shapes. You can make square waves by adding sine waves together. That's not what we're talking about here. In this chapter, we're adding waves of identical frequency onto each other and looking at the result. The secret to doing it, to adding the sinusoidal waves to each other, is going to be to follow the phasor method, illustrated by some examples. So here I've got y1. It's a cosine graph, but shifted to the right with a initial phase angle of 30 degrees. And I'm adding it to another cosine graph, which is shifted to the left with a phase angle of 60 degrees. So I have to add them up. Now remember that each one of these sinusoidal functions can be thought of as a phasor, like a vector. I'm recalling the connection between circular motion and simple harmonic motion. Okay, so what I have here is y1 I would draw in a phasor diagram at minus 30 degrees. That's y1, minus 30 degrees. And then it has length 20, by the way. And then y2 is at 60 degrees, and it has a length of 40. Something like that. That's y2 at 60 degrees. Now remember that y1, it's actually a function of time. So y1 actually goes back and forth sinusoidally. In the phasor diagram, it spins around at angular frequency omega. So does y2. So although this is only the picture at t equals 0, they both rotate at the same rate, and so the relationship between them stays the same. So I'm going to add up y1 and y2. You can do it just like you add vectors. I'll stick y2 onto the end of y1, the head to tail method of adding them up. So here's y1 and here's y2, like so. This one's y1, this one's y2. What I care about is the resultant, which is the sum of the two. Right there. That's the resultant y. So now you see the connection that we had hints of that connects it to a right triangle. I have a right triangle here. Here's the right angle. What I care about finding is the phase. So the goal of this is I'm trying to write y1 plus y2 as just a new sinusoidal function with some amplitude that I have to find. And I know it's going to have the same frequency, but it has some phase that I don't know. So I'm trying to figure out in my picture what A is, the length of the resultant, and I'm trying to figure out this angle right there. That's the phase angle. It's not the angle from y1, it's the angle from the x-axis. Okay, so you can just do it geometrically. First, the amplitude is easiest. The amplitude, just use Pythagorean theorem. It'll be the square root of 20 squared plus 40 squared, which comes out to be 44.7. So I just get a new sinusoidal function whose amplitude is 44.7. The phase angle, there are two steps to it. First, I figure out what this full angle is using arctangent. So I'll call that one theta or something. A theta would be arctan of 40 over 20, which is arctan of 2, which is 63.4 degrees. But what I care about is the angle phi, which is that minus 30 degrees. This is negative 30 down here. So I get 33.4 degrees. So putting it all together, it's just telling me that I can add y1 and y2, these two sinusoidal functions, using just a graphical method. The resultant of the two is going to be equal to 44.7 in amplitude, and it's a sinusoidal function, same frequency, cos omega t, but it has a phase angle, which is a positive 33.4 degrees. Probably you'd want to use radians because omega is going to be in radians, but just for geometric purposes, it's more clear to use angles. So in that example, I got a right triangle because the two individual phasors differed by 90 degrees. That isn't always the case. In the next example, I have two sinusoidal functions. They don't differ by 90 degrees from each other, but I can still draw the phasor diagram and figure out how to add them up. In this example, I have a phasor with a phase of plus 10 degrees and another one with a phase of plus 50 degrees. So I'll sketch them separately first. This one's at 10 degrees. The second one has same amplitude, but it's at 50 degrees. That's y1 and 2, and I have to add them together. I'll take 2 and put it onto the end of 1. So there's 1. And then 2, slide 2 over onto the end of it. I'm gonna extend this line and stick number 2 on here, like so. Same length. Now, phasor number 2 is at 50 degrees, which means it's 40 degrees from phasor number 1. Okay, now I'm trying to add these two together, so I draw the resultant, like so. And I care about two things. I care about the amplitude, and I care about the phase angle from the axis, phi. Okay. First of all, this is an isosceles triangle. It's got two equal sides. That means that these angles here on opposite sides, they're both equal. And in fact, they're both equal to 20 degrees. This is called the exterior angle theorem, which is that the exterior angle, which is 40, is equal to the sum of the two interior angles that are opposite to it. Since they're equal, they both have to add up to 20, and they both have to add up to 40, which means since they're equal, they both have to be 20 degrees. Okay, so I know the angles inside of the triangle are 20 degrees. That will let me figure out what the phase angle is. The phase angle, therefore, is going to be 30 degrees. So I'm done with that part of it. The phase angle must be 20 degrees in the triangle, plus 10 degrees from y1. So that's 30. Okay, I'm done there. I need the amplitude. Now, there's no right triangle, so I can't use Pythagorean theorem. However, what I'll do is split this triangle in half. And what I notice is the amplitude is made of 2 times the base of these triangles. In other words, the amplitude is equal to twice. And how long is each base? Each base is cosine of 20. Actually, it's 8 times cosine of 20. It's 2 times 8 cos 20. Which comes out to be 15. So there we go. We've got our resultant. We can write it down. The resultant of y1 and 2 is equal to 15.0 cos omega t plus phase, which is plus 30 in this case. So again, I took two sinusoidal functions, same frequency, and I added them up using the phasor method. A valid question here is, why don't I just use trig identities to add them up? And you certainly could. You know that there are identities to add sine or cosine and cosine together, the sum to product formulas. You'll of course get the same answer as what we did in this case. The reason that I'm showing you this method is because later on we'll be adding multiple waves onto each other. Waves of the same frequency but from multiple sources, not just 2, but like 3, 4, n of them. And it's very useful. So once you have more than 2, the formulas aren't helpful anymore. You need some graphical way to visualize what happens when the waves add up. And so that's why it's important to understand how the phasor method works. Now, it is only helpful when the waves are of the same frequency. Like both of them have to be cos omega t. In this next example, we're adding two waves together, but they're oppositely moving waves. One of them's going, y1 is traveling to the left, and y2 is traveling to the right. That means that y1 is of the form kx plus omega t, the other one's kx minus omega t. So it's as if one of them has a negative frequency compared to the other. which means I don't use the phasor method to add them up. I would just go straight to the sum to sum to product formulas to figure out the resultant. So here we have to add y1 and y2, and we want to figure out what the combined wave looks like. We'll find the result is very surprising. So I add them up. I use the sum to product formulas for adding sine of alpha plus sine of beta, and I get 6.00 sine of pi x times cosine of 0.6 of pi, pi times 0.600 t. What does this mean? I added two traveling waves together. Y1 is a wave traveling to the left. Y2 is a wave traveling to the right. When I added them up, the thing that I get doesn't look like a traveling wave at all. It's not of the right form, right? It's not of the form kx minus omega t. So what do I have here? The animation shows us clearly what happens. Here's the red, here's y1, here's y2. When you add them up, the two waves don't produce a traveling wave at all. It's what we call a standing wave. Notice how at some moments the peaks line up, and so you just get a big amplitude there. At other moments, the peaks and the troughs line up, and it's just a flat line. There's no displacement of the string at all. But the peaks don't move anywhere. They stay fixed in place. Okay, so we call this a standing wave. It's a very special type of wave which can result when two oppositely moving waves meet each other. Notice that what makes it so different from the traveling waves is you see each one of these has an amplitude of 3. That's it. Just the amplitude is 3 for each one of those individually. However, this standing wave, the amplitude of the wave is different depending on what value of x you're at, like we see here. For example, at this point right here where the cursor is, there is always an amplitude of 0. We call those places where the amplitude stays 0, those are called nodes, N-O-D-E. They're called nodes. You can think of it like they're no displacement. On the other hand, like this point right here, where the cursor is, that's a place of maximum displacement. In fact, the amplitude is 2a at those places. We call those locations antinodes, where you get the greatest possible amplitude when the waves combine. So in other words, there's a new feature here, which is that the standing wave has an amplitude which is a function of x. The amplitude as a function of x is 6.00 times sine pi x. So in question A, we're asked to determine the maximum transverse position of an element of the medium at these different x values. Well, that's exactly what we would plug in. This is the maximum transverse position. Of course, it goes up and down. That's what the function of time tells you. As time goes on, the actual displacement changes up and down. But the peak value is given by just this 6 sine pi x. So we'd plug in the A, B, and C different x values to get the amplitude of those 3 positions. In part D, we have to find the 3 smallest values of x corresponding to antinodes. Antinodes, remember, that means the locations, it's asking for the x values of maximum displacement. In this case, it's the max displacement of 6. The places that have amplitude 6 are the amplitude the antinode positions. So in part D, we're asked to locate the antinodes. So what values of x do you get the peaks? Well, remember, sine function has a peak at pi over 2, 3 pi over 2, and so on. So our antinode positions are going to be at x equals a half, 3 halves, 5 halves, and so on. In this problem, we're given the standing wave, and we have to figure out what the component waves are that produce it. Along the way, we'll draw a graph of the standing wave, identify the wavelength and frequency, and so on. So first, prepare a graph showing y is a function of x for 5 different times. So when I'm drawing y of x, I can't ignore the cos omega t part of it. I have to consider that as well. So let's first draw a sketch of what it looks like at t equals 0. At t equals 0, cosine is equal to 1. And I just have a graph of 6 sine kx. So here's y as a function of x. And it's just a sine function. This is 4 meters right here. Let's see what we get at 5 milliseconds. At 5 milliseconds, you can check that this cosine part is equal to 0. Why is that? Well, let's look at cosine 100 pi t. So now I want to draw just the time part of it. At t equals, so this is just a cosine graph. It looks like this. In fact, since omega is equal to 100 pi, the frequency is equal to 50 hertz. You can check that f, which is omega over 2 pi, is 50 hertz. In other words, the period, 1 over 50, is 20 milliseconds. Okay, so this is 20 milliseconds here. This is 5 milliseconds. This is 10. This is 15. And it repeats again after 20. So at t equals 0, cosine's at its maximum. And we just get the sine graph. At t equals 5 milliseconds, it's 0. The cosine part of it is equal to 0 at 5 milliseconds. So at 5 milliseconds, just a flat line. Nothing to see. Y of x, just a flat line. Actually, that also is true at 15 milliseconds. It's y is equal to 0. What about at 20 milliseconds? Well, at 20 milliseconds, oh, I missed 10. At 10 milliseconds, the cosine's equal to -1. So y of x at 10 milliseconds is, it gives you a minus sign from the cosine. So I have a graph of -6 sine of pi over 2x. Just a minus sign graph. Like so. Okay, that's what it looks like at t equals 10. By the way, it's the same graph at 20 milliseconds as it is at t equals 0. So this is typical of a standing wave. The peaks just stand in place and go up and down. We saw that before. There's a standing wave. The peaks just go up and down in place. It doesn't travel anywhere. Identify the wavelength. Well, we can read it off from the graph. That is a 4-meter wavelength. Of course, you can also find the value of k to be pi over 2 and find that therefore lambda is 4 meters that way too. From the graph, identify the frequency of the wave. Well, we could do that here. After 20 milliseconds, the graph has repeated itself. That means the period is 20, or we did it mathematically solving for the period. Okay, Then finally, determine the two component waves which combine to produce this standing wave function. The standing wave in pink is made of a left moving wave plus a right moving wave. Our job is to write down exactly what the two functions are. So in this case, we're given the standing wave function. We're given it to be sine times cosine, which means that it is sine of alpha plus sine of beta. We can write down exactly what it must be here. If y is 6 sine kx times cosine omega t, that means the two individual waves, y1, must be 3 sine pi over 2 x minus 100 pi t. That's the right moving wave. And y2 is just the left moving version of that. 3 sine pi over 2x plus 100 pi t. Notice that the individual waves have half the amplitude as the standing wave does, but they have exactly the same wave number, wavelength, and the same angular frequency and period. Just one is traveling to the right and the other one is traveling to the left. You can check based on the sum to product rule that you get the correct standing wave given those two separate traveling waves.